In this part 2 video of mechanical properties, we are going to see about the tensile test conducted on the mild steel specimen. As a result, stress strain curve is obtained and the components of the stress strain curves are discussed. So coming to the classification of mechanical tests, there are different types of mechanical tests performed on the specimen to characterize the material. The different types of stress induced are tensile stress, compression stress, shear stress and torsional stress. So all these stresses are induced by universal testing machine. Second one, the rate at which the stress is induced. We can induce the stress gradually or we can induce the stress suddenly. When the stress is induced suddenly, it is called impact stress or impact load. Then third one, the number of times the stresses are induced, that is cyclic stress in the case of a fatigue. So coming to the importance of the mechanical properties, if the material is stiffer, it is difficult to bend. If the material is stronger, it resists the plastic deformation. If the material is light, it is used in the application where having the high strength to weight ratio. If the material is tougher, it is hard to break. So to identify all these properties like stiffness, strength, lightness, that is weight, lightweight, and toughness, we want to identify with the help of the mechanical testing. So coming to the mechanical testing, we will be identify the properties like strength, stiffness, hardness, and toughness. So the strength, stiffness, and toughness is characterized by the stress strain curve. So stress strain curve is obtained by loading the specimen in the universal testing machine and stressing it using the tensile force. So the body elongates, at the same time the diameter reduces until the failure happens. So coming to the tensile test, it is conducted how much the material is stretched before the material breaks. The figure shows the stress strain diagram for the mild steel specimen where the point D shows the necking and the point E shows the fracture point. So from this tensile test or from the stress strain curve, we can able to identify the material strength, stiffness, elasticity, plasticity, ductility, brittleness and toughness. So in the tensile test, the material is subjected to pulling or tensile forces and the behavior of the material is tested. That is the characterization of the pulling force is determined. At the same time, the stress to strain is plotted. Once the material is stretched, before it is about to fail, the object, the neck is formed. So the tensile test is conducted in the universal testing machine. The load is converted into stress value and the displacement is converted into strain value. Here we'll be taking the dog bone specimen shape and it is loaded in the space provided for the tensile test. So pulling force is applied at the both ends until the specimen fails. Once the pulling force is applied, the body elongates. At one particular time, the neck is formed. That indicates the maximum strength of the material. Beyond that, if you increase the stress, the object will fail. So this stress strain curve is unique for the particular material. So from the tensile test, we will be getting two kinds of curves. One is load displacement curve. The second one is stress strain curve. From the load displacement curve, we can identify the elongation of the particular material. Once the elongation is high, we can tell the material is ductile. If the elongation is less, we can classify it as a brittle material. And from the stress strain curve, we can identify the material properties like Young's modulus, whether the material is elastic or plastic, and we can determine yield strength and ultimate tensile strength, and we can describe the ductility, brittleness and toughness nature of the material, and finally the strain hardening characteristics. So coming to the load displacement curve, once the load is applied, the body elongates. So here it is a plot representing the displacement in the x-axis and the load in the y-axis. So when the load increases, the displacement also increases. At the final point, the fracture occurs. So in this graph, the approximate load of around 300 Newton is registered and the elongation about 5.5 mm is registered. So we can tell the displacement is 5.5 mm. If the different test is conducted, the same test is conducted for the different material which has the displacement of 3 mm, we can tell that particular material is less ductile. So from the load displacement curve, we can able to find out the elongation property of the material. So from the elongation, we can able to classify the material as ductile material or brittle material. So the elongation is the degree at which the material is stretched or compressed prior to rupture. So it is the point on the tensile strength and the yield strength, and it is represented as the percentage of the original length. So in this picture, we can see the elongation up to the elastic limit. You can strain it as an elastic strain. Then beyond the yield point, we can tell it is an plastic strain. So in the plastic strain, we'll be having uniform plastic deformation and also non-uniform plastic deformation. So here it is a representation of different materials having the different elongation. So in the first picture, we can see if the elongation is less, we can classify it as a brittle material. If the elongation is more, the factor of 10, it is classified as a ductile material. So polymer foams have more elongation, rubber have more elongation, polymers have more elongation, then wood have very less elongation, then composites have medium elongation, the metals have the elongation up to 0.9 factor, and ceramics, porous ceramics and glasses, that is all the things which comes under this yellow color, classified as a ceramics. Ceramics is having a brittle nature, so the elongation is very less. So this is the bubble graph showing the plot between strength and elongation. Here we can able to classify the different materials like rubber, polymers, metals and alloys, composites, ceramics and glasses, wood and wood products, their variation in strength and elongation. So here we can tell rubber have more elongation, polymers and composite stands in the middle. So coming to the stress strain curve, to get the stress strain curve, you will be pulling the material and the characteristics are recorded. So we are applying the tensile load, stress is increased, as a result of stress, strain is increased, and the plot between stress and strain is recorded, and this curve is called stress strain curve. So in the model stress strain curve, we can see the points like O, A, B, C, D and E. So up to the starting from the point O to A, this line represents the Young's modulus. The slope of this line represents the Young's modulus, which measures the stiffness of the material. So this slope, the ratio of stress by strain, is constant up to the point 0 to A, and this material behaves like a elastic material up to the point A. And the end of the line A, that is under the line OA, it deviates and it forms a light curve. So it indicates after this proportional limit, the material is about to yield. Then the next point is from A to B. So the B point is the elastic limit or the yield strength limit. The small curve, it is from A to B, it is a small curve deviating from the point A. So here also, the material continuously behave like a elastic material, but the ratio of stress to strain is not a constant. So up to OAB, the material will be in the elastic region. Coming to the part B and C. So B is the upper yield point. So at this point, the material yields and the plastic stage starts. So in this point, even though the material is, the load is removed, the material doesn't comes back to its original shape. So the plastic stage starts at the point B and the point C is the lower yield point. Coming to the next part, from C to D, we are continuously increasing the stress. The upward curve, it indicates the specimen, it is regaining its strength. At the point D, the necking will happens. So the cross-section area decreases suddenly at one point. So that point is recorded at point D and it is called the breaking stress and it is the maximum stress also. And we can tell this point as an ultimate strength or ultimate tensile strength. About this point, beyond this point, even though if you increase it, right, a small amount of force is enabled to break the material or to make the material to fail. At one point from D to E, the material fractures. So D to E is a downward curve. So D represents the ultimate tensile strength, or the point it represents the neck formation, and at this point that cross-sectional area of the material is reduced, and E is the point, fracture point. With minimum load, the material fails at that particular point. So from this stress strain curve, we can able to find out the tensile strength. So from point D, project an horizontal line, it represents the stress in the y-axis. So we can tell the strength we can measure, and we can measure the stiffness. Stiffness is nothing but the measure, it's a Young's modulus. So once you calculate the Young's modulus, if the value of Young's modulus is very high, we can tell the stiffness is high. Then we can tell the elastic limit and the plastic limit, and we can tell the ductility nature of the material and also the brittleness nature of the material. Finally, the toughness. Toughness is nothing but the impact strength. The impact strength can be measured in two ways. One by the impact test, second with the help of the stress strain curve also we can measure. We can enclose the area obtained by these points. The area enclosed by these points will give you the impact strength or toughness. So after neck formation, if you increase the load, the cavities are formed. Micro voids or cavities gets formed. Beyond that, if you increase the limit, the cavities get joined and cavities cracks get growth, join and crack is formed. That is crack initiation. Then the crack is propagated and finally the fracture occurs. So the mode of fracture of a ductile material is a cup and cone fracture. So the neck formation, crack initiation, crack propagation, and finally the cup and cone fracture. So from the stress strain curve, we can able to classify the material is ductile material or a brittle material. Here there are two curves representing the stress strain curve of a ductile material and the brittle material. So in the ductile material, you can see the material is yielding and you have the ultimate point and finally the fracture. But in the brittle material, material yields, after that ultimate is registered, at this point the material breaks. So this is the best, I can tell the best example is glass. Once you apply the force, it breaks suddenly without any warning. The best material for the example for the brittle material is glass and cast iron. Similarly, for the ductile material, mostly all the materials, metals, mild steel, aluminum, copper, rubber, and some of the plastics behave ductile in nature. So this ductile material have a long life compared to the brittle material, and manufacturing process like rolling, forging, and wire drawing and bending. So this process can be employed to the ductile material. But brittle material, the mode of manufacturing is only by casting, and you can experience a high percentage of elongation in a ductile material and low percentage of elongation in a brittle material. So from the stress strain curve, we can able to classify the material as elastic, plastic material, ductile material, on brittle material. And also we can classify whether the material is ceramics based or whether it's a metal based. All the ductile materials comes under the metal base, and polymers having very low elasticity and toughness is also very less. Ceramics high strength but toughness is very less. Ductile materials medium strength, moderate strength with high toughness. So from the stress strain curve, we can able to classify the material is stronger or stiffer, whether it is an elastic or a plastic material, whether it is a ductile material or whether it is a brittle material or a tougher material. So from the stress strain curve, we can able to find out the elastic limit, the plastic limit. We can see the Hooke's law justification, and we can find out the Young's modulus, and we can find out the different strengths like yield strength, ultimate tensile strength, fracture strength, working strength, proof stress, and strain hardening, and finally the fracture or failure point. So this elastic deformation is caused by stretching of the bonds between atoms, and when the deformation is reversed and the load is removed. But in the plastic deformation, you apply the load, deformation is formed, and you release the load, the regaining of its shape is not happen. So the plasticity nature exists. So from the stress strain curve, you can see the elastic region and the plastic region. So coming to the Hooke's law, we can state that Hooke's law, within the elastic limit, the stress is proportional to the strain, or strain is proportional to the stress. So up to this elastic limit, you will be seeing a proportional line, straight line, increasing in nature with respect to stress and strain. So it obeys, the line obeys the Hooke's law. So sigma represents stress, epsilon represents strain, and E represents Young's modulus. So we can state that E is equal to stress by strain, Young's modulus. So this Young's modulus is the slope of the line in the elastic deformation stage, and it represents the stiffness of the material. When the stiffness is more, the material is hard to deflect. So here there are different stress strain curve for the different materials, ranging from polypropylene to titanium carbide. The slope of the polypropylene material is very less compared to the titanium carbide. So it states that titanium carbide has high Young's modulus and the polypropylene has a low Young's modulus. And also we can tell polypropylene has very low stiffness compared to titanium carbide. So higher the Young's modulus, higher the stiffness of the material. So here it shows the bubble graph of variation of Young's modulus with respect to density of different materials like timber, foam, polymers, ceramics, metal and alloys and ceramics. And from this value we can take that the Young's modulus for the timber is 10 gigapascal. Young's modulus for the cast iron is 40 to 50 gigapascal. And Young's modulus for the carbon epoxy composite is nearly 220 gigapascal. So the value of carbon epoxy composite is very high. For this reason only, the carbon epoxy composites are used in sports bikes and also cycles, right, for the frames in the cycles, where we require lightweight and also the stiffness should be very high. So the high stiffness material is difficult to bend or deform. So from this graph we can tell the higher Young's modulus, more is the stiffer, less the Young's modulus, more it is flexible. So the importance of the Young's modulus, you can see the wings of the plane, aircraft, right? It bends due to the air force, air current. So it indicates that the wings lacks stiffness. So we want to select a material with high Young's modulus for that particular part to avoid failure. So coming to the strength, there are different types of strength like tensile strength, compression strength, shear strength, torsional strength, flexural strength, and bending strength. Buckling strength. So coming to the tensile strength, it is the ability to withstand the tensile force. Compressive strength is the ability to withstand squeezing or compressive force. Shear stress, shear strength is the ability to withstand shear force. Torsional strength is the ability to withstand twisting or torsional force. Flexural strength is the ability to withstand the bending force. And buckling strength is the ability to withstand the buckling force. So usually the buckling will occur in the long columns where the slenderness ratio is very high. L by D ratio is very high. The thickness is very less compared to very less compared to the length. So strength is the ability of the material to withstand the load without failure. So the highlighted region indicates the neck formation. Finally, the fracture occurs. Neck formation is shown and finally the fracture occurs. So strength is defined as the force per unit area. So from the stress strain curve, the maximum point, that is a necking point, you can take it is an ultimate tensile strength. So the force recorded at this point is taken divided by the area of cross section of the specimen. It is given as strength. So the unit of strength is megapascal or pounds per square inch. So we will be conducting a test on the universal testing machine. We will be stretching the specimen to obtain the graph. So from the graph, we can able to find out the ultimate tensile strength. So here we can see the strength of the different materials where polymer and foams registers very low strength. We can tell it is a weaker material. Similarly, rubbers and some polymers, pure polymers, is also weak. Once this polymers is employed to make a composites, the strength is increased from 50 to 1600 range megapascal. And wood products have very low strength because due to the absorption of moisture, it is expected to have the very low strength, and metals and alloys have the more strength. Glasses and ceramics have registered strength greater than 10,000 megapascal. So coming to the yield strength, after the elastic limit, even though if the load is not registered or the load is not applied, right, the material will yield to upper yield point and then to lower yield point. So it is the indication that after or at the point or up to the point of the yield, the material will be elastic. Beyond yield, the material is said to be plastic. So that indicates the material deforms and it changes its size and shape so that it cannot able to regain its shape when the load is removed. So at this point, we will be telling it as an yield strength. So this yield strength is an indication of material's plastic deformation. So for a material, for a aircraft to the wing, for an example, the wing to be very straight, we need a select a material with high yield strength. Then only the material or the part doesn't bend plastically. So coming to the factor of safety, it is very important to select a material, safer material for particular applications. So the stress capable of preventing the failure is called working stress or allowable stress. So the risk is reduced when the safety is enhanced. So the material engineer's property role is to select a material which will not fail at that particular limit. So the factor of safety is defined as the ratio of ultimate tensile strength to the working strength for the ductile material. So here we can see the importance of the factor of safety. Suppose the working stress is around 100 megapascal. We can select some of the composites and we can select some of the metals and alloys and we can select all the glasses and all the ceramics we can select. But we cannot select polymers, rubbers and foams because it falls below the limit. So it is treated as a weaker material. Even though if you select also, the material will or the part will fail, causes the accidents. Finally, the fracture strength, it is the last point. It represents the final load or the stress at which the material fails. So the material is failed at the end of the plastic deformation. So coming to the toughness, toughness is very important property of the material. So toughness is the ability of the material to resist breaking under the action of shock or impact loads. So toughness is the combination of strength and ductility. So when the material is tough, it is very hard to break. So the lack of toughness indicates the brittleness. So in this stress strain curve, we can see the area enclosed by the brittle material is very less, and the area enclosed by the ductile material is very high. So that we can tell the ductile material has very high toughness compared to the brittle material. So the larger the area indicates the more toughness of the material. So the brittle material has very low toughness like ceramics, and the ductile material has very high toughness. All the metals comes under the ductile material, and plastic material have very low toughness. So the toughness value indicates the performance under the shock loads. Low toughness indicates brittleness. So coming to the strain hardening or work hardening or cold working, from the stress strain curve, we can able to make the metal harder and stronger through plastic deformation from the yield point to the maximum stress, that is ultimate stress. So in the stress strain curve, the point number 2 and point number 3, between this stress, that is yield stress and the ultimate tensile stress, if the material is strained continuously, the material gets work hardened. So this is called strain hardening or work hardening. So in the cold working of metals, increasing the stress produces the ultimate plastic deformation and makes the metal become stronger and more difficult to deform. For example, making of a knife or the sword from the iron. So this knife and sword is very hard and tough after being cold worked. So these are the equations to remember. We know stress is the ratio of load to area. Strain is the ratio of change in dimension to the original dimension. And from stress and strain, we can able to find out the Young's modulus. Young's modulus is stress by strain. Then coming to the longitudinal strain, that is along the axis, the change in length to the original length. Coming to the lateral strain, traverse to the axis, that is nothing but the diameter. It may be a diameter or breadth or thickness, the ratio of change in diameter to the original diameter. Now we can find out the change in length del L equal to PL by AE, and Poisson's ratio is the ratio of lateral strain to the longitudinal strain. So the stress at the elastic limit is load at the elastic limit divided by initial area. So yield stress is yield load by initial area. So true stress, we can define it as instantaneous load by instantaneous area. Suppose for example, we want to measure the true stress at the point C. We want to measure the load at the point C and also the area of the specimen recorded at the point C. It is the instantaneous point, true stress and true strain. Then ultimate stress is the maximum load by area, and safe stress is the ratio of ultimate stress to the factor of safety. And finally, the percentage of elongation in length. While the material is pulled, the length is elongated and the diameter is reduced. That is, you can get the increased area, increased in length and decreased in area. So we can able to find out the percentage elongation in length and percentage reduction in area using these two equations. So in this lecture, we have seen what is proportional limit and what is elastic and plastic limit, Hooke's law, Young's modulus, stiffness. In the strength, we have seen yield strength, proof strength, ultimate tensile strength, and finally the fracture strength. And we have seen what is safe working stress and factor of safety and strain hardening. And from the stress strain curve, we can able to find out the strength of the particular material, stiffness of the material. Yeah. We can able to find out the material characteristics like elasticity, plasticity, ductileness and brittleness and toughness. And we have seen what is engineering stress and strain and true stress and strain. Thank you.